Yes, all of you. Is my voice audible? Please respond in chat.
Yes, sir.
Hello. All right. So in the last class, we were discussing about casting process. Let's try to give you a recap about what we have discussed. So we have discussed about casting. So what is casting? It's a process of producing products by pouring molten material in a mold cavity of desired shape and size and is allowed for solidification. Upon solidification, the solidified component called casting is removed out of the mold cavity. That we call it as casting process. So we have discussed about different types of casting process. I mean to say, the classification part of casting. One is expendable casting process, and second one is permanent casting process. And we have discussed about different types of sand casting process and mold making process and different types of bindings. And we have also discussed about different types of molding sands. Sorry, different types of sand molds. And in the last class, we stopped at core. So what is a core? Core is a solid sand body used for producing castings with internal cavities. What is a core? It is a solid sand body used to produce castings with internal cavities. Now, so we discussed about cores and cores are of, I said core is a solid sand body used for producing castings with internal cavities. And cores are of two types. One is green sand core, second one dry sand core. Green sand core, second one is dry sand core. Now let's talk about these two different types of. Let's talk about these two different types of cores. As I told you, so core is a solid sand body used to produce castings with internal cavities. And these are of two types. One is green sand core, second one is a dry sand core. So green sand cores are produced by the pattern itself during the process of mold making. Now let's say, for example, if you wish to produce any casting with an internal cavity, if you wish to produce any casting with an internal cavity. Now, let's say, for example, let's say this is a casting, or this is a casting. If you want to have this casting with an internal cavity, now let's say, for example, to produce a casting like this, or let's take it as a cubicle body, cubicle casting. Now, to produce a cubicle casting with a vertical cylindrical internal hole with the dimensions diameter d and height h, diameter d and height h. Now, to produce a casting, cubicle casting with the dimensions, with a vertical cylindrical internal hole with the dimensions d and h, what I do is I prepare a pattern with the same dimensions and I make a vertical cylindrical internal hole with the same dimensions d and h. Now, this pattern is having a vertical cylindrical internal hole with the dimensions d and h, where d stands for diameter, h stands for height. Now, I place this pattern inside the mold flask and I pour molding sand. Now I pour molding sand, I ram it. Now once the molding sand gets tightly consolidated around the pattern, we invert the molding flask and we remove the pattern out of the mold cavity. Now when the pattern is removed out of the mold cavity, pattern comes out, leaving the sand within the cavity, leaving the sand within this internal cavity in the mold cavity itself. That sand, solid sand body will be left within the mold cavity itself. The sand stick which is left within the mold cavity is called as a green sand core. Is called as what? green sand core. Now we pour molten material into the mold cavity. Now once the mold cavity is completely filled with the molten material, we allow it for solidification. Now once it gets completely solidified, we remove the casting out of the mold cavity, and we also remove the green sand core out of the casting. So thereby we'll be able to produce the casting with the vertical, cylindrical, internal core. And in this particular process, whatever the core that is used is called as green sand core. Now we are very clear that green sand cores are produced by the pattern itself during the process of mold making, and we do not produce green sand cores separately. So these are produced by the pattern itself during the process of mold making. And the green sand codes, the main limitation of green sand code is it can be used only for simple internal cavities, not for complex cavities. Now, when it is to produce complex cavities for castings, we shall go for dry sand cores. Now, let's talk about a dry sand core. Now, for example, if you wish to produce a complex internal cavity, now to produce complex internal cavity, what we do is we produce the core of desired shape. We produce the core of desired shape and size, and we bake this core at 110 to 240 degrees centigrade. Now, once the core is completely baked, it is appropriately placed within the mold cavity. Now, once it is appropriately placed, now let's say to place the core appropriately in the mold cavity at the desired locations, it's going to be very difficult. Now, to place it appropriately within the mold cavity without shifting of the core from its position, means to place the core. Now, for example, if this is a core, to place this core inside the mold cavity, once the core is placed in the mold cavity, this core should not shift from its position like this or like this. So shifting of the core from its position results in defective casting. And to avoid this defect, what we do is we provide supports on either sides of the core to place it appropriately within the mold cavity so that shifting of the core from its position can be avoided. And these supports, which are provided on either sides of the core, are called as core prints. What do we call them? Core prints. And when the size of the core is more, and whenever we go for complex core, sometimes we may have to provide supports for the core within the mold cavity. Now, whenever it is to provide supports within the mold cavity, we provide supports for the core within the mold cavity itself like this. And these supports are called as chaplets. These are called as chaplets. Remember, chaplets are the metallic components which are used to support the core within the mold cavity. Very important. Chaplets are the metallic components which are used to support the core within the mold cavity. When somebody asks you, what is the object of a core? So what is the object of a chaplet? What is the object of a chaplet? To support the core within the mold cavity. That is the object of the chaplets. Now, once it is appropriately placed within the mold cavity, and when it is supported with the chaplets within the mold cavity, when the moment we pour the molten material into the mold cavity, molten material surrounds chaplets. So when the hot molten material, which is poured at around 1500 degrees centigrade, is and surrounds these chaplets, the moment the chaplets get surrounded by the molten material, by the hot molten material, due to heat transfer, these chaplets would start undergoing melting. And by the time it gets completely solidified, these chaplets would become an integral part of the casting on solidification. So because of this reason, whenever chaplets are used, ensure that the chaplets are made of the same material, same as the casting material. I mean to say, if cast iron casting is carried out, chaplet should be made of cast iron, because chaplets would become an integral part of the casting on solidification. So this is about cores. Am I clear so far? Please respond.
Yes, sir.
So chaplets, so cores are the solid sand body. Core is a solid sand body used to produce castings with internal cavities. This you have to remember. So please take a note. Just a minute. Please make a note. Cores. Right. Core is a solid sand body. Are you able to see the screen? Please make a note from cores. Core is a solid sand body up till here. Core is a solid sand body used to produce. Core is a solid sand body used to produce castings with internal cavities. Castings with internal cavities. Next, cores are of two types. Cores are of two types. First one, green sand core. Second, dry sand core. Green sand core. Second one is dry sand core. Next, please make a note of this. Green sand core is formed by the pattern itself. Green sand core is formed by the pattern itself during the process of mold making. During the process of mold making. These cores are made of sand. These cores are made of sand, same as the molding sand. Same as the molding sand. Next point. Green sand cores can be used to produce, please make a note. Green sand cores are used. Green sand cores are used to produce simple internal cavities. To produce simple internal cavities. Next. Next. Complex cavities. Complex cavities are produced by using dry sand cores. Complex cavities are produced by using dry sand cores. Next point. Dry sand cores are produced separately. Dry sand cores are produced separately. Dry sand cores are produced separately, comma, baked at 110 to 240 degrees centigrade. Baked at 110 to 240 degrees centigrade. And are appropriately placed within the mold cavity. and are appropriately placed within the mold cavity and are appropriately placed within the mold cavity. Next, core prints are provided. Core prints are provided. Core prints are provided on either sides of the core. Core prints are provided on either sides of the core to avoid shifting of the core. To avoid shifting of the core from its position. To avoid shifting of the core from its position. Next. For complex cavities, for complex cavities, chaplets may be provided. For complex cavities, chaplets may be provided. Next. Chaplets are the metallic components Chaplets are the metallic components used to support the core. Chaplets are the metallic components used to support the core. Used to support the core within the mold cavity. Within the mold cavity. Next point. Whenever chaplets are used, whenever chaplets are used, ensure that they are made of the material. They are made of the material same as casting material. They are made of the material same as casting material. Same as casting material. You please take this diagram. Please take this diagram fast. Done. Have you drawn the diagram? Right. Next, take subheading properties of molding sand. Properties of molding sand. Properties of molding sand. So whenever we produce castings, we should look at before carrying out the casting process, we should look at the various properties of molding sand. Now, during the process of casting, whenever we look at the properties of molding sand, so we have got different types of we have got different properties of molding sand. One is grain size and shape properties of sorry porosity or permeability, refractoriness, housiness or strength. Next one is adhesiveness, plasticity, and collapsibility. Now look at this, the grain size and shape. So the size and shape of the grains in the sand determine the application of various types of the foundry. Now we have got different types of the grain sizes. One is fine, medium, and coarse. Now look at the usage. Now, fine grains are used for producing small and intricate castings. Medium are used for bench work and light floor casting process. And the coarse grains are used for larger castings. And, uh, and the next one is permeability, permeability or porosity. Now, look at this. Now, so once the mold cavity is produced, we pour molten material in the pouring basin. Now, molten material passes through the sprue and reaches sprue base well, and finally it reaches the mold cavity. Now, once the mold cavity is completely filled with the molten material would start flowing through a riser. The moment we observe the flow of molten material in the riser, we would stop pouring the molten material because flow of molten material in the riser is an indication that the mold cavity is completely filled with molten material. So remember, flow of molten material is always an indication that the mold cavity is completely filled with molten material. Now look at this. Now at the time of pouring the molten material into the mold cavity or into the pouring basin, molten material at the time of pouring will be in direct contact with the atmosphere. Thereby, the molten material reacts with all the unwanted gases or atmospheric gases and would react with all those gases and would mix up with all those gases and would reach the mold cavity. Now, once the mold cavity is completely filled with the molten material, we allow it for solidification. Now, when it is allowed for solidification, by the time it gets completely solidified, all those unwanted gases should leave the mold cavity. Now, the point of discussion is, would these gases leave the mold cavity or not by the time it gets completely solidified? If that is the question, it's very difficult for these gases to leave the mold cavity because it is completely fixed. But if these gases remain within the mold cavity, it results in defective casting, and there is no point in carrying out the casting process. So, for these gases to leave the mold cavity, we need to provide some facilitation for these gases to leave that mold cavity. అంటే ఫర్ ఎగ్జాంపుల్ అంటే మనం తెలుగులో చెప్పుకోవాలనుకోండి, ఇప్పుడు మన ఇంట్లో దొంగ పడ్డాడు అనుకోండి, బయట లాక్ చేస్తే దొంగ తప్పించుకోలేడు కదా. సో ఫర్ హిమ్, ఫార్ ద థీఫ్ టు ఎస్కేప్, వాట్ షుడ్ వి డూ? వీ షుడ్ ప్రొవైడ్ వన్ మోర్ డోర్, ఇంకో డోర్ ఓపెన్ చేసి పెట్టాలి, అప్పుడే వాడు తప్పించుకోగలరు, అంతే కదా. సేమ్ సేమ్ హియర్, సేమ్ అప్లైస్ హియర్. నౌ లుక్ అట్ దిస్. So that facilitation for these gases to leave the mold cavity is provided by the molding sand itself, and that ability of the molding sand to allow these unwanted gases to leave the mold cavity is called as permeability or porosity. Now porosity, I define it like this. Porosity or permeability is the ability of the molding sand to leave the mold cavity through the pores of the molding sand, or to escape through the pores of the molding sand. That ability of the molding sand to allow the unwanted gases to escape through the pores of the molding sand is called as permeability or porosity. Very, very important. And the next one is, and before stepping into the next one, uh, always permeability is measured in terms of permeability number, capital P. So permeability number is measured, or it is calculated with the formula VH by PAT. Now look at this, where P is permeability number, capital P is permeability number, capital V volume of air passing through the test specimen in cubic centimeters. H is height of the test specimen in centimeters. Small p means this one. Pressure of air in grams per centimeter square. A, cross-sectional area of the test specimen. And small t is time taken by the air to flow through the specimen in minutes. So time is in minutes here. So this is the formula to be used to calculate permeability number of the molding sand. Remember, very important. So to calculate a permeability number of the molding sand, we need to have the entire data VHPAT. If in examination, if any of the data is missing out, and if P and T are given, then permeability is calculated using the formula 501.28 by PT. If P is also not given, then it should be calculated using the formula 50.128 by T, and P is taken as 10 grams per centimeter square, where it is the standard value. And the next very important property of the molding sand is strength or coarseness. Strength or coarseness. Now, strength or coarseness is the ability of the molding sand to hold the sand grains together. To hold the sand grains together. That we call it as strength or coarseness. This one, strength or coarseness. And always, when you look at permeability, permeability depends on, or permeability of the molding sand always depends on two parameters. One is sand, and the second one is grain size. So if the percentage composition of sand is more, permeability will be more. And if the sand grain, size of the sand grain is more, larger the sand grains, permeability will be higher. Now, when it comes to strength or coarseness, strength of the molding sand always depends on the density of the molding sand. If density is higher, strength will be higher. And also depends on two more parameters. One is clay, the other one is grain size. If grain size is smaller, strength will be higher. If clay content is higher, strength will be higher. Smaller the grain size, strength will be higher. Higher the clay content, strength will be higher. Now, when you look at these two parameters, when you compare these two, strength and permeability, both are opposite. When you try to increase the permeability, strength will go down, and when you increase the strength, permeability will go down. So both are opposite. And the next one is refractoriness. So what is refractoriness? Ability of the molding sand to withstand the higher temperatures of the molten material. We know that we pour molten material into the mold cavity at higher degrees of temperature. Sometimes it may be at 1000 degrees centigrade, or sometimes 1500 degrees centigrade, or sometimes beyond that. Now, when we pour molten material at such high degrees of temperature, the molten material, molding sand, which is in direct contact with the molten material, should be able to withstand those higher temperatures of the molten material. Otherwise, it results in defective casting. So that ability of the molding sand to withstand those higher temperatures of the molten material is called as refractoriness. Next, adhesiveness. What is adhesiveness? Adhesiveness is nothing but sticking property. So we know that the mold cavity is prepared within the mold flask, correct or not? So whenever we pour molding sand, the molding sand should be able to stick to or adhere to the container walls or mold flask walls. Otherwise, we cannot carry out the casting process. We call it as adhesiveness. So adhesiveness is what? Ability of the molding sand to stick to the container walls or mold flask walls. And the next one is plasticity or flowability. So this is plasticity. Plasticity means of flowability is the ability of the molding sand to reach each and every corner of the mold flask. I will call it as plasticity or flowability. And the next one is collapsibility. Collapsibility. So collapsibility normally is referred to easy breakdown of the molding sand at the time of removal of the casting out of the mold cavity. But apart from that, there is one more objective of collapsibility, and there is one more reference for collapsibility. That is, see here, with respect to the cores, already we discussed about cores. So with respect to cores, collapsibility is the ability of the molding sand to reduce its volume by itself to some extent to accommodate the compressive forces. See here, whenever cores are used and when allowed for solidification, so we know that molten material contracts on solidification. So whenever the molten material contracts on solidification, molten material on contraction produces compressive forces, correct or not? And these compressive forces are exerted or generated on the core. So whenever compressive forces are exerted on the core like this, core should be able to reduce its volume by itself under the compressive forces generated due to contraction of the molten material during the process of solidification. And this ability of the molding sand is called as collapsibility. If the material lacks the property collapsibility, no doubt in it, it results in defective casting. Because if the core cannot accommodate these compressive forces, it results in centerline shrinkages. Or internal cracks. And the next property we have is, of course, the listing is over, but there is one more property called coefficient of expansion. Coefficient of expansion. So coefficient of expansion is now already we discussed. We pour molten material at higher degrees of temperature. So whenever molten material is poured into the mold cavity at higher degrees of temperature, so heat transfer takes place between the molten material and the molding sand that is in direct contact with the molten metal. So due to heat transfer, the sand layer tends to expand in this direction. Look at me. So molten material, the molding sand layer, which is in contact with the molten metal, tends to expand like this. But expansion of the sand layer like this is restricted by the container walls. But due to heat transfer, the sand layer tends to expand in any of the directions possible. And the possible direction of expansion of the sand layer is into the mold cavity itself like this. If the molding sand layer expands into the mold cavity like this, it results in defective casting. Now tell me, coefficient of expansion for the molding sand should be higher or lower? Coefficient of expansion should be higher or lower? Answer. Anybody? Coefficient of expansion for the molding sand should be higher or lower? Is anybody listening? So coefficient of expansion should always be low. Should always be low. Please take a note. Properties of molding sand. Properties of molding sand. Properties of molded sand. Take down the first one. Grain size and shape. Please take down this. Please take down what is written on the screen. You're done with this. Take down this. Next, put subheading porosity or permeability. Porosity or permeability, right on. It is the ability of the molding sand. It is the ability of the molding sand. It is the ability of the molding sand to allow the unwanted gases, to escape through the pores of it, to escape through the pores of it. to escape through the pores of it. Now you please write down. Look at the screen. Write down. Look at the screen and please copy this. Permeability is measured in terms of permeability number, capital P. Write it in brackets, capital P. Permeability is measured in terms of permeability number, capital P. And permeability number, capital P is equal to VH by PAT, where V is volume of air passing through the test specimen in CC, small h, height of the test specimen, small p, pressure of air in grams per centimeter square, capital A, cross-sectional area of the test specimen, small t, time taken by the air to flow through the specimen in minutes. Please copy this. Next. We're done with this. Write down. Permeability number. Permeability number can also be calculated. Permeability number can also be calculated using the following relations. Permeability number can also be calculated using the following relations. Look at the screen. Please take down these two. Capital P is equal to 50.128 by T. Capital P is equal to 501.28 by PT. Done. Now look at the next and add two more points. Very important. Permeability depends on permeability depends on sand silica and grain size. Permeability depends on sand silica and grain size. Write down. If sand silica is more, under that write down. If sand silica is more, if sand silica is more, permeability is more. Permeability is more. Next one. If grain size is higher, if grain size is higher, if grain size is higher, permeability is higher. Permeability is higher. Now, now put subheading. Strength or causaleness. Look at this. Strength or causaleness. Look at the screen for spellings. Under the try down. It is the ability of the molding sand. It is the ability of the molding sand to hold the sand grains together. It is the ability of the molding sand to hold the sand grains together. Next, it depends on it depends on density. It depends on density, clay content, clay content, and grain size. Clay content and grain size. Now write down. If density is more, if density is more, strength is more. If density is more, strength is more. Next, if clay content is more, if clay content is more, strength is more. Strength is more. Next, smaller the grain size, smaller the grain size, strength is higher. Smaller the grain size, strength is higher. Now, next, put subheading adhesiveness. Look at the word right now. Adhesiveness. Adhesiveness. Right up. It is the ability. It is the ability of the molding sand. It is the ability of the molding sand to adhere. Ability of the molding sand to adhere to the container walls. To adhere to the container walls. Next, put subheading plasticity. Look at the board. Look at the screen. Plasticity. It is the ability of the molding sand molding sand to reach each and every corner of the mold flask. Each and every corner of the mold flask, and take the required shape on ramming. Next, now look at screen right now. Refractoriness. Refractoriness. Right now, it is the ability of the molding sand. It is the ability of the molding sand to withstand ability of the molding sand to withstand the higher temperatures of the molten metal. To withstand the higher temperatures of the molten metal. Higher temperatures of the molten metal. Next, it depends on grain size. It depends on grain size. If grain size is more, if grain size is more, refractoriness is more. If grain size is more, refractoriness is more. Next, put subheading collapsibility. Look at the screen right on collapsibility. Look at the screen and please take down this collapsibility. Under the right is to collapse after solidified matter is to be taken out from the mold. Under the right now. Next, add one more point. With respect to cores, with respect to cores, it is the ability of the molding sand. It is the ability of the molding sand to reduce its volume by itself. To reduce its volume by itself to some extent. Reduce its volume by itself to some extent. To some extent. Under the compressive forces generated, under the compressive forces generated due to contraction of the molten metal, due to contraction of the molten metal during solidification. Contraction of the molten metal during solidification. Next, write one more. Next property. Put subheading coefficient of expansion. Coefficient of expansion. Under that, write down It should be low. Coefficient of expansion should be low. So I hope you are comfortable with the discussion happened today. Are you comfortable with the discussion happened today? All of you, please respond. Or we shall stop it here for today. Stop it here for today. Meet you tomorrow as per the scheduled time. Thank you.